Hello, this is the second video in our fluids unit entitled Hydrostatic Pressure. And the essential question is, why do fluids exert pressure? And what does this pressure depend on? So the third fluid variable that we want to define is pressure, which is represented with a capital uppercase P. Pressure is defined as the amount of force that is exerted on a square meter of surface area. And the equation that comes out of that definition is pressure is equal to F over A. That equation shows that we have a linear relationship between pressure and force. So the higher the force, the higher the pressure. And an inverse relationship with area and pressure. So the lower the area, the higher the pressure. We like to do a demo in class where people touch hands. So go ahead and just do this in front of yourself. Put your hands together. You'll feel some pressure, one hand on the other. The harder you push, right, the more pressure you feel. That's kind of self-explanatory, but increasing force increases pressure. If you double the force, you double the pressure. But the other way to increase the pressure is to change the area of contact. This is a lot of surface area. If you change it to a finger and then push, you're going to feel a lot more pressure even for the same amount of force because the area got really small, so the pressure goes up. This equation is really relevant in the real world. It explains why we have sharp needles at doctor's office. It would be a real bummer to have a needle that was dull because of the relationship between area and pressure. And it also explains why airplane windows are so small, because if they were bigger, the glass would have to resist a lot more force and it would be more likely to break. It also tells you what you should do if you happen to be on a frozen lake and break through the ice. You want to spread your body out over as much area and lay down, crawl across the ice as you possibly can so that you don't push as hard on any little piece of the lake. In physics, the standard unit of pressure is the Pascal, which is equal to a Newton per meter squared. Force, of course, is measured in newtons, and area is measured in meters squared. So Newton per meter squared is the same as 1 Pascal. Hydrostatic pressure is defined as the pressure on an object from the fluid that is surrounding it. You may not have realized this, but you're actually experiencing hydrostatic pressure right now because you are surrounded by a fluid. The fluid is air, just like the bird that's shown in that diagram. You probably have noticed hydrostatic pressure if you've ever been swimming, however. When you go to the bottom of a pool and you feel that pool water pushing in on your ears, that's another example of hydrostatic pressure. So what causes hydrostatic pressure? Well, fundamentally, it's caused by the fact that all objects are trying to be pulled down by Earth's gravitational force field. The molecules in the air, the molecules in the water, everything is trying to get closer to the center of the Earth. So fluids will actually settle as close as they can to the center of the Earth. And they keep going downwards until some other molecules or objects repel them or hold them up, right? So the water is kind of being repelled or held up by the ground there, the bottom of the ocean, and the air is being held up by the water. So they're trying to get down, but they can't get any further because they're being held up by the things underneath them. Now, if you're that bird and that fish kind of pinned in between, you are feeling the forces of those molecules around you pushing and being pushed by each other as they try to settle closer to the center of the Earth. So you feel a pressure on you from all the molecules that are pushing down, trying to get to the center of the Earth. So what variables are going to determine the magnitude or the size of the hydrostatic pressure from an object? I'd actually really encourage you to pause your video for a second and think about what do you think we're going to see in this equation? If I asked you to calculate how much hydrostatic pressure is acting on you right now versus maybe the amount that would act on you at the bottom of the swimming pool, what variables do you think you would need to know about the scenario to make that calculation? Okay, you're back. Hopefully you did put some thought into it, because understanding these equations really comes from you guys trying to take a deep and meaningful look at your own lives and trying to recall and predict things based on your own experience. In any case, there are 3 variables that are going to be in this equation. The first, which probably a lot of you came up with, has to do with the amount of the fluid that's above you. So if you're under a small amount of water, for example, a small h of the fluid column above you, you experience a small amount of pressure because there's only a handful of those things on top of you pushing down, right? There's only a small number of things that are trying to get down through you to the center of Earth. Whereas if you're at the bottom of a column of fluid, you got a whole pile of stuff on top of you, you're going to be experiencing a lot more pressure. So the bigger the height of the fluid column measured above the object, the more hydrostatic pressure you're going to feel. This means that there is a linear relationship between H and P because there's more fluid molecules pushing down on the object, the higher the H. The second variable that determines the magnitude of the hydrostatic pressure is the density of the fluid. So when you go swimming in something like water, water is actually a relatively low density fluid, and that means it doesn't really hurt when you go underwater, too much at least if you don't go too far. So the smaller the density, the smaller the pressure. If you tried to go swimming in, for example, liquid mercury or molten lead, for a variety of reasons, it would hurt. But one of those reasons is because the higher the density of the fluid, the more pressure you're going to feel as well. There's a linear relationship between density and pressure because obviously there's more mass above you if you have a higher density fluid. And the third variable, which maybe a handful of you guys came up with, but probably not everybody, is the strength of the gravitational force field on the planet. In other words, if you're on a planet that doesn't have a ton of gravity, like for example Earth, you don't feel as much pressure because the water molecules above you or the fluid molecules above you aren't being pulled on that hard by the planet. If you went somewhere else, like for example Jupiter, that has a massive amount of gravity, and you had the same amount of the same fluid on top of you, you would feel a lot more pressure because Jupiter would be pulling that fluid down on top of your head a lot harder than Earth does. So there's a linear relationship between G, which is the planet's gravitational force field, and the pressure, because each fluid molecule on top is pulled harder down when we have stronger gravitational fields. So one thing that's kind of different about hydrostatic pressure compared to, say, regular mechanical pressure, when we were talking about our hands pushing on things, has to do with the direction that hydrostatic pressure acts. Because fluid molecules can be shifted around and poked out of the way, like I demonstrated with the meter stick in the last video, hydrostatic pressure is the same in all directions. It pushes up, down, left, and right. So if you pick a point in space, the pressure is actually acting all around that point, on that point, not just in one direction. This is different than like the elephant standing on the high heels, which only acts downwards. Pressure acts in all, or hydrostatic pressure acts in all directions. We can see this if you've thought about the way bubbles look as they rise up in a fluid. They're definitely smaller down here when it's really deep because we have a lot more hydrostatic pressure based on that linear relationship between H and P. There's a lot more pressure, but that pressure acts in all directions. So our bubbles are still relatively spherical. As we rise up in the fluid column, the pressure on each bubble goes down because there's not as much fluid on top, but it still acts in all directions equally, which means our bubbles are still spheres. They keep their shape. It's not like flattened pancakes that you would see if that pressure only acted down. So what if you have a container that has a bunch of different fluids in it? Like, for example, this one, which I'll give you a little hint, has 2 different fluids plus 2 solids in it. Well, the pressure at any location in that column is going to be equal to the sum of the hydrostatic pressure contributed by each fluid above the object. That means you can just add up the pressure of everything above you to figure out how much pressure is acting on you. If you wanted to know the pressure on the bottom of this container shown, it would be the pressure from the honey, plus the pressure from the syrup, plus the pressure from the soap, plus the pressure from the water, plus the pressure from the veggie oil, plus alcohol, plus lamp oil, and then I'm adding air because there's actually another fluid on top of that column. That would give you your total pressure. So it's pretty straightforward if you have multiple pressures in the same container. All right, we're finally ready to see our hydrostatic pressure equation and see if it matches up with all of the relationships and predictions that we've made. So on your equation sheet, you'll see P equals P naught plus rho GH. And in this equation, that P is the hydrostatic pressure that we've just been talking about due to a fluid that is around us, and it's measured in pascals. So hydrostatic pressure equals P naught. That little 0 kind of means initial or at the start. In this case, it's referring to the pressure at the top of the fluid. And And this may be another fluid that's on top pushing down, like that last example where we had air on the top. So you'd have to add, that's basically the air pressure you'd be adding into everything. Or it could be a solid object that's on top. So maybe you have a piston on top of a container of fluid of some kind, and you're pushing down on that piston or pushing up on the piston. That could also be the pressure that we're talking about. So whatever kind of mechanical pressures on the top, that's P naught. And then these are those three relationships that we kind of came up with a few slides ago. We got linear relationships with the density of the fluid, the gravitational field, and the height of the fluid. A couple things are underlined in that definition because they're common mistakes. Sometimes people forget that that rho is the density of the fluid, and they'll use the density of some other object nearby, so it's important to realize that this is all about the fluid. And then that h is notably the height above the object, not the height of the object from the ground. So you've got to be a little bit careful about that. The last thing you need to know about hydrostatic pressure is a couple definitions. You may see the terms absolute pressure and the terms gauge pressure. In this equation, the absolute pressure is like the total pressure that an object is feeling. That includes the atmospheric pressure around us. So if you're asked for absolute pressure, probably you're going to be calculating P, and you're going to be substituting in 101 kilopascals as your P naught value. And that's because most objects on Earth have the atmosphere pushing in on them, plus whatever fluid you're concerned with in the problem, which is usually water. Usually these are things underwater. And so you're doing that. This is the pressure from the air, and then this would be the absolute pressure from the water. And you would find P naught, or P, being your total pressure. Some problems, however, ask for a different kind of pressure. Since most objects on Earth have this 101 kilopascals of atmosphere pushing on us, sometimes it's just annoying to have to add 101 kPa to every single problem. And so they've made another term called gauge pressure, which is basically the same equation but ignoring the atmosphere. So if you're ever asked to find gauge pressure, don't worry about that 101 kPa, just do the pressure due to the fluid without that extra kPa from the atmosphere. Okay, we've come to the end of this show. Please take a few minutes and revisit the essential question, which is, why do fluids exert pressure, and what does this pressure depend on? Thanks for watching.